Have you ever stopped to think about what actually happens to data before it powers your favorite app? You know, it's not magic. It's actually a really structured and honestly a fascinating journey. So today we're going to follow a single piece of data from its raw, messy state all the way to a powerful prediction through something called the machine learning pipeline.
So that brings up the big question, right? How does a machine really learn? It's not like you just flick a switch and poof, you have an AI. No, it's a very methodical process. And in this explainer, we're going to pull back that curtain and walk through every single step that powers so much of the technology you use every single day.
So here's our roadmap for this whole journey. First, we'll look at the blueprint, the pipeline itself. Then we'll get our hands dirty and forge our foundation by cleaning the data. After that, we get creative with something called feature engineering. Then we'll test its strength in the gauntlet of training. And finally, we launch our creation out into the world.
All right, so just like any great construction project, you've got to start with a blueprint. Before we can even think about building a model, we need to understand the master plan, the machine learning pipeline.
So what is it really? Well, you can think of it like an assembly line, but for data. Raw, messy, chaotic information goes in one end, and at each step along the way, it gets refined and transformed until a valuable, useful prediction comes out the other side. And the real key here is that this process is automated and repeatable, which is crucial for consistency. And here are the exact stops on our map. We start by defining the problem, what are we even trying to solve? Then we pre-process the data, engineer features, train and evaluate the model, and finally, deploy and monitor it. This is the path that pretty much every successful model follows, so let's take our first real step.
You know, just like a house, a machine learning model is only as strong as its foundation. And for us, that foundation is built by taking messy, raw data and making it absolutely pristine.
Okay, so the data we start with usually comes in one of two flavors. On one hand, you've got structured data. This is the neat stuff, organized in rows and columns, just like a spreadsheet. On the other hand, you have unstructured data, the messy, free-form stuff like social media posts, emails, or even images. Both are incredibly valuable, but both need a lot of prep work before a machine can make any sense of them.
And this brings us to a fundamental truth that, believe me, every data scientist learns the hard way. Real-world data is dirty. It is almost never ready to use right out of the box, because it's coming from countless different sources with different standards, and that creates a whole host of problems.
So what does dirty data actually look like? Well, it can be incomplete, think missing values, like an empty occupation field. It can be noisy, with obvious errors or outliers, like a salary of just 10. It can be inconsistent, with contradictory information, like an age that just doesn't line up with a birthday. And sometimes the mess is even intentional, like when a system requires a birthday, so everyone just puts in January 1st to get past the screen.
So how do we fix this mess? We have a whole toolkit for this. For missing data, a common trick is to fill in the blanks with an average value. And since machines only understand numbers, not words, we have to encode things like yes and no into 1 and 0. And to make sure that one big number doesn't get way too much attention, we scale all the numbers down to a common range, like 0 to 1.
Okay, so once our data is clean, we move on to what many people consider the most creative part of the entire pipeline: feature engineering. This is where we go from just having data to having meaningful information.
This is really the art of choosing the right signals for our model to focus on. For example, if we want to predict whether a student will pass an exam, we don't just give the model their name. We engineer features, like hours studied or class attendance, things that actually have predictive power.
And this right here really gets to the heart of it. The quality of your features is everything. You could have the most sophisticated, complex model in the world, but if you feed it garbage information, it's totally useless. But with clever, meaningful features, even a very simple model can achieve incredible results.
So how do we pick the best features? We've got a few strategies. Filter methods are kind of like a quick and dirty statistical check. They're fast. Wrapper methods are slower, but they're way more thorough, because they use a model as a test driver for feature combinations. And then embedded methods are a kind of hybrid, building the selection right into the training process itself for a nice balance of speed and accuracy.
All right, our data is clean and our features are engineered. It is time for the main event, the climax of our data's journey, putting the model through the gauntlet of training and evaluation to see if it has truly learned anything.
Now, the single most important rule here is that we can't test a model on the same data it learned from. That would be like letting a student study the exact questions on the final exam. Sure, they might get a perfect score, but do they actually learn anything? To know for sure, you have to test them on questions they've never, ever seen before.
And this is exactly how we do it. We split our data set into two parts. The vast majority, usually around 80%, becomes the training set. This is the data the model studies to learn patterns. The other 20% is the test set, and it's held back, kept completely separate. This is the final exam.
Now, during that training phase, we're not just feeding the model data, we're also fine-tuning its settings. These are called hyperparameters, and you can just think of them as the knobs on a machine. We're carefully adjusting these knobs to find the perfect combination that gives us the absolute best performance.
But as we're tuning those knobs, we face this central challenge. On one side, there's a risk of overfitting. This is where the model learns the training data too well. It basically memorizes every detail, including all the random noise. It gets an A+ on the training data, but then fails spectacularly on the test data. On the other side is underfitting, where the model is just too simple and fails to capture the underlying patterns at all. It does poorly everywhere. The goal is to find that perfect balance right in the middle.
So how do we make sure our model's good performance wasn't just a lucky guess on one specific test set? We use a powerful technique called K-fold cross-validation. Long story short, instead of giving it one final exam, we give the model multiple different exams, using different parts of the data each time. This gives us a much more reliable and stable score of its true ability to generalize.
Our model has been trained, it's been tested, and it has proven its worth. The data's journey is almost complete. It is time for the final stage, the launch.
And this is deployment. It's the moment we move our model out of the research lab and into the real world. We integrate it into an app, a website, or some other business system where it finally gets to do its job on new, live data. But deploying the model is not the final goodbye. In fact, the journey's never really over. Once a model is live, it has to be constantly monitored. The world changes, new data comes in, and a model that was incredibly accurate yesterday might not be so accurate tomorrow.
And this leaves us with the final critical question that anyone working with AI has to constantly ask themselves. When a model's performance starts to drop, what's to blame? Is it the data? Is it the model itself? Or has the world simply changed? That constant cycle of questioning, well, that's what keeps this entire field moving forward.
Welcome to the Deep Dive.
You know, it's amazing how things like streaming recommendations just get you, or how spam filters work so well. It feels like magic.
It really does.
Yes.
But behind that magic is a very structured process.
Exactly. And that's what we're diving into today, the machine learning pipeline. It's basically the A to Z journey data takes to become, well, smart enough to make those predictions. Our mission here is to break down this complex sequence. We're using a great source, lecture notes from Dr. Lakshmini Abeywartana at the Sri Lanka Institute of Information Technology to guide us. Think of this as your shortcut to understanding how these AI systems get built. Okay, let's unpack this.
Yeah, what's fascinating, I think, is that understanding this pipeline is key for anyone curious about AI. It shows how it all connects from the initial idea right through to making it work in the real world. It streamlines everything.
So where do we even begin? Before touching data, before code, what's step one?
Well, the absolute first thing is problem definition.
You have to know exactly what problem you're trying to solve and why. Is it predicting customer churn, identifying spam, recommending movies? Without a clear goal, everything that follows is kind of pointless.
Aimless, yeah, like building a car without knowing where you want to drive it.
Precisely. It saves so much wasted effort down the line, ensures you're building something actually useful.
Right, so problem defined. Now we need to fuel the data. What types are we talking about and where does it come from?
Good question. So, data collection. Broadly, data comes in two flavors, structured and unstructured.
Okay.
Structured data is the neat stuff. Think spreadsheets, databases, rows and columns, easy to search, organized.
Gotcha.
Unstructured is well, everything else. Text and emails, social media posts, images, audio files. It doesn't have that neat table format.
Makes sense. And how do people actually get this data? Do they just download it?
Sometimes,
Right.
but often it involves using sources of data like APIs.
APIs, right? Those interfaces between programs?
Exactly, like pulling weather data or Twitter feeds. Then there are databases, of course, SQL, NoSQL, and just plain files, CSVs, Excel sheets, JSON, XML.
And tools to get it.
Yeah, there are specific data acquisition tools, things like web scraping tools, Beautiful Soup or Scrapey to pull data from websites, API clients like Postman, and for bigger jobs, ETL tools.
ETL.
Extract, transform, load. Think of them like data pipelines before the main ML pipeline. They grab data, clean it up a bit, and load it where it needs to go. Tools like Apache NiFi or Talent handle that.
Okay, so we've gathered a mountain of data.
Yeah.
But you mentioned earlier, raw data isn't exactly clean, is it? Our source says it's often messy.
Oh, messy is putting it mildly sometimes. That's why data preprocessing is so critical. It's all about cleaning, fixing, and formatting that raw data.
Why is it so important? Can't the computer just figure it out?
Unfortunately, no. Machines need numbers, and they're very sensitive to weirdness in the data, missing values, errors, inconsistencies that can completely throw off a model. Honestly, data scientists often spend most of their time just cleaning data.
Really? More time cleaning than building the actual model.
Absolutely. It's maybe less glamorous, but it's foundational. The quality of your preprocessing heavily impacts the final result. The AI's intelligence really starts with clean data.
Okay, so paint a picture of this mess. What does incomplete, noisy, or inconsistent data actually look like?
Sure. Incomplete is easy just missing values. Like an online form where someone didn't fill in their occupation, sometimes it's hidden, like everyone having a birthday of January 1st because the system required something.
Oh, okay.
Noisy data means errors or outliers. Imagine a salary field accidentally entered as $10 instead of, say, $100,000. Or maybe a sensor giving a wildly incorrect reading.
Right. And inconsistent.
That's when things don't match up. Like the system says someone's age is 42, but their entered birthday makes them 35. Or maybe ratings using different scales, like 5 stars in one place and 10 in another for the same product. It's surprisingly common.
Wow, okay. That does sound messy. So how do you fix all that? What are the steps in preprocessing?
Well, first, handling missing data. You've got options. You could fill the gaps with the average value for that column, the mean, or maybe fill it with 0 or a special marker like unknown.
Or just delete the record.
Yeah, if a row has too many missing values, sometimes dropping it is the best option.
Yeah.
Then you need to handle converting categorical data.
Because machines need numbers, not words.
Exactly. So if you have categories like yes, no, you might use label encoding, turn yes into 1, no into 0. Simple.
Okay.
For categories without an order, like countries, UK, India, USA, one hot encoding is common. You create new columns. Is UK, is India, is UA with 1s or 0s?
Right, so each category gets its own switch.
Pretty much. There's also target encoding, which is a bit more advanced. You replace the category name, say neighborhood A, with the average of the thing you're trying to predict, like average house price, for that category. It gives the model a useful hint.
What else?
Scaling the data. This is vital. Imagine one feature is age, maybe ranging from 10 to 80, and another is exam score from 0 to 10.
The age numbers are much bigger.
Right. And without scaling, the model might think age is more important just because the numbers are larger. So scaling puts everything on a similar range. Min-max scaling squeezes values between 0 and 1. Standardization, or z-score scaling, reshapes it so the average is 0 and the standard deviation is 1.
So it treats all the features fairly.
Exactly. It prevents certain features from unfairly dominating the learning process.
Okay. Data prepped, cleaned, scaled. Now, I've heard this term feature engineering. It sounds important. Our source even says good features can make simple models powerful. Why is it such a big deal?
Feature engineering. This is where things get really interesting, maybe even a bit creative. It's about taking your clean data and transforming it, or creating new features from it to make it even more informative for the model.
So it's not just cleaning, it's enhancing.
Yeah, exactly. Think about predicting if a student will pass an exam. Your raw data might have hours studied, lectures attended, sleep hours. Those are your initial features. Feature engineering might involve creating a new feature, like study intensity, hours studied divided by days before the exam, or maybe combining attendance and sleep into a preparedness score.
I see. You're crafting better ingredients for the model.
That's a great way to put it, and that quote is spot on. Even a basic model can work wonders if you feed it really well-engineered features. Conversely, a super complex model can fail miserably if the features are poor quality or irrelevant. You're guiding the machine.
So it's about smart choices, picking the best info, improving it, maybe removing junk to help the machine learn better. How do you know what the best features are?
That's the million-dollar question. It's often a mix of domain knowledge, understanding the problem area, and experimentation. The features are just your columns, your variables, but raw features aren't always optimal. Some might be redundant, some noisy, and sometimes the most predictive information comes from combining features.
Okay, so how do you select the best ones? Is there a process for that?
Yes, that's called feature selection. It's about picking the most useful features and discarding the less useful ones. It reduces complexity and can improve performance.
What are some ways to do that?
There are several methods. A simple one is variance threshold. If a feature barely changes across your data set, like if all students attended 100% of lectures, it's probably not very predictive.
Yeah.
So you might drop features with very low variance.
Makes sense. If it's the same for everyone, it can't explain differences.
Exactly. Then there's mutual information. This measures how much information a feature shares with the target variable, the thing you're trying to predict. It's good because it catches nonlinear relationships too, like how attendance might link to passing.
Okay.
You also have methods like select k-best or select percentile. These use statistical tests to score features, and then you just pick the top k features or the top, say, 10%, like picking your top 5 ingredients, as the source says.
Nice analogy.
And finally, there's model-based selection. Some models, like random forests, can actually tell you which features they found most important during training. It's like the model itself helps you choose.
That's very cool. So different approaches.
Yeah.
Are they categorized somehow?
Yeah, they generally fall into 3 buckets: filter, wrapper, and embedded methods.
Okay.
Filter methods are fast. They look at the statistical properties of the data itself before any model training. Good for a first pass on big data sets. Wrapper methods use a specific model to evaluate subsets of features. They wrap the selection process around a model. More accurate, potentially, but much slower.
And embedded?
Embedded methods build feature selection right into the model training process. The model learns which features are important as it learns the task. It's often a good balance between speed and accuracy.
Got it. Now, what about dimensionality reduction? Is that just another name for feature selection?
Good question. They're related, but different. Feature selection picks from your existing features. Dimensionality reduction transforms your features into a smaller set of new, combined features.
Ah, okay. So it's more about compressing the information.
Exactly. Think of having hundreds or thousands of features. Dimensionality reduction techniques, like PCA principal component analysis, try to find the main patterns or components that capture most of the information, allowing you to represent the data with fewer dimensions without losing the essence, like summarizing a long article into bullet points.
Okay, that distinction makes sense. So we've got pristine, well-engineered features. Now for the main event, the model. What is a machine learning model, really?
In simple terms, a model is like a mathematical representation or a set of rules that the computer learns from the data. During training, it figures out the patterns connecting your input features to the output you want to predict. It's the recipe it learns.
Yeah, there are tons of different models. How do you choose?
Yeah, the choice depends on several things. What's the problem type? Classification, regression, clustering. How much data do you have? Some models need more data than others. Do you need to explain how the model makes decisions? Some are black boxes, others are more transparent.
Right, like for medical diagnosis, you'd want explainability.
Absolutely. And then there's the trade-off between accuracy and speed. Do you need the absolute best result, even if it takes time, or is a slightly less accurate but faster model better for your application?
Lots to consider. Okay, model chosen, time to train it. This is where the learning happens, right?
Yeah,
How does that work?
It is. So you take your prepared data. The first crucial step is splitting the data. You typically divide it into a training set, maybe 80%, and a test set, the remaining 20%.
Why split it?
You use the training set to actually teach the model. It looks at the features and the known outcomes in this set and adjusts its internal workings, its parameters, to find the patterns. The test set is kept completely separate. You only use it after training to see how well the model performs on data it's never seen before. It's like giving the student the final exam after they've studied.
Got it. Prevents the model from just memorizing the answers.
Exactly. During training, The model iterates, trying to minimize its errors on the training data, essentially learning the relationship between the inputs and outputs.
You mentioned hyperparameters earlier. What role do they play here? Are they learned too?
No, that's the key difference. Parameters are learned by the model from the data. Hyperparameters are settings you configure before training starts.
Like knobs you can tune.
Perfect analogy. They're like the learning rate, the complexity of the model, like the number of layers in a neural network, or the number of trees in a random forest. Tuning these knobs is critical. The right settings can massively boost performance, prevent overfitting or underfitting, and make training more efficient. Choosing the wrong ones can really hinder the model.
So finding the right hyperparameter settings is a big part of getting good results.
A very big part, yes. It often involves experimentation.
Okay, but how do we ensure that our single train-to-split didn't just give us a lucky or unlucky result? How do we know the performance is reliable?
Excellent point. That's where cross-validation comes in. It's a technique to get a more stable and reliable estimate of how your model will perform on unseen data.
How does it work?
The most common type is k-fold cross-validation. You divide your entire data set into, say, k5 folds or parts. Then you train the model 5 times. Each time you use 4 folds for training and 1 fold for testing. Crucially, you rotate which fold is the test set each time.
So every part of the data gets to be the test set once.
Exactly. Then you average the performance scores from those 5 runs. This average gives you a much more robust idea of the model's true performance than a single train-to-split. There are variations like stratified k-fold, important for unbalanced data, but the core idea is repeated testing on different subsets.
That sounds much more reliable.
Oh.
Okay, so after training, tuning, cross-validating, we finally evaluate the model properly. Why is this step so critical?
Evaluation tells you if all that work actually paid off. Did the model learn useful patterns, or did it just memorize the training data? Does it generalize well to new, unseen situations? You need solid metrics to answer. Is it accurate? How often does it make mistakes? Is it fair across different groups?
Right. It's the reality check.
Absolutely. A model might look great on paper or on the training data, but fail spectacularly in the real world if not evaluated properly against unseen data. It's the ultimate test.
What are the main things that can go wrong here? What pitfalls do we look for?
The 2 classic pitfalls are overfitting and underfitting.
Okay, break those down.
Overfitting is when the model learns the training data too well. It picks up not just the underlying patterns, but also the noise and random fluctuations specific to that training set. It becomes too complex. So it performs brilliantly on the training data, but poorly on the test data because it can't generalize.
It memorized instead of learned.
Exactly. Underfitting is the opposite. The model is too simple. It fails to capture the underlying patterns even in the training data. So it performs poorly on both the training and the test data. It just hasn't learned enough.
So the sweet spot is a good model that learns the real patterns and generalizes well.
Precisely. It finds that balance complex enough to capture the patterns, but not so complex that it fits the noise. Good performance on both training and, more importantly, test data is the goal.
Okay, fantastic.
Yeah.
We've navigated the whole process, built and evaluated a solid model. It works. Now what? Just release it into the wild.
If only it were that simple. The next step is deployment. This means taking your validated model and making it available for actual use.
So getting it out of the lab and into the real world.
Exactly. It needs to run reliably outside your development environment. Maybe it becomes part of a website, an app, an internal company tool. This often involves setting up servers, creating APIs for others to call the model, ensuring it can handle the load, things like that. It's a significant engineering step.
It sounds like deployment isn't the end of the story either.
Definitely not. That leads us to post-deployment, monitor and maintain. This is crucial and often overlooked. Once a model is live, you have to keep an eye on it.
Why? Doesn't it just keep working?
The world changes. The data it sees in the real world might start to look different from the data it was trained on. This is called data drift. User behavior changes, new trends emerge. This can cause the model's performance to degrade over time.
So its accuracy can drop.
Yes, so you need continuous monitoring. Are predictions still accurate? Are there unexpected errors? You also need to collect user feedback, fix bugs, and, very importantly, plan for retraining the model periodically with fresh data to keep it up to date and effective.
It's like maintaining any complex system. It needs ongoing care.
Exactly. It's a life cycle, not a one-off project.
Wow. So pulling this all together, this whole pipeline, it really highlights how much goes into these AI systems we interact with daily. It's not just one magic algorithm.
Not at all. It's a rigorous process involving data understanding, cleaning, creative feature engineering, careful modeling, thorough evaluation, and ongoing maintenance. Understanding these steps, I think, helps appreciate both the power and the potential limitations of AI. It's built, refined, and constantly adjusted by people.
So here's a final thought for you, our listener. Considering how much careful work goes into each stage, defining the problem, cleaning the data, crafting features, training, evaluating, deploying, and then continuously monitoring, how might understanding this pipeline change the way you think about or even trust the AI recommendations or decisions you encounter every single day?
And if you want to dive even deeper, the source material mentioned Hands-on ML with Scikit-Learn and TensorFlow by Aurélien Géron, and also Pattern Recognition and Machine Learning by Christopher Bishop. Both are excellent. They're quite technical resources.